Good morning, everyone. Thank you for the invitation and introduction. So my name is Amir Tamasebi. I'm the Senior Director for Machine Learning AI at Codametrics, who's a spin-off from Partners Healthcare. Today, what I thought I could do based on the time given, just have a review about the AI enabling natural language processing and the advancement that we have seen during the last couple of years, which is flying really quickly, and kind of link it to the healthcare applications and see how that can help with the healthcare challenges we are facing. I guess it's going to be a bit of a switch. So far, we have been mainly talking about the autonomous driving and then the interesting talk about the new chips. So this is more going towards another aspect of the data, which would be textual data. So if I could get by raise of hands, how many people deal with textual data? Okay, so that's pretty good. Let's get started. So for those of you who are not familiar or not heard much about natural language processing, it's basically the human's attempt to teach a machine, first of all, to understand the human language and also try to generate a human-like conversation or a piece of text. In terms of how far we have gone, basically, probably you guys have heard about the fake news, which is the most recent things going on about the advancement in the natural language processing. But also, I thought I could show a quick demo where the state of the art is with respect to AI-driven NLP. So there is this kind of a group working on a technology driving NLP, which referred to as transformers. So I have a quick demo. Excuse me, do you mind bringing up the website so we can have a quick look? So what this engine does behind the scene, there's a humongous amount of data being trained to replicate human language. So what you will see here is that you choose a sentence or two, you start with that, you can type anything you want, and the machine tries to continue the conversation from where you left off. So in this example, you can see the part that starts from the quotation. That's all generated automatically by a machine. In some examples, looks very realistic, which is kind of cool, but also scary. But that is basically related to the fact that there's a lot of computation required to get to this point, as well as a ton of amount of data to show to the machine. Can we go back to the slides, please? So what does NLP advancement mean for healthcare domain? So of course, many of us are visiting doctors from one occasion to another, or go for an imaging. Every visit that is done by a physician, usually the information about the patient is being captured in a piece of text. And that text is kind of the most common way of communication between one doctor to another, between the hospital, between the patient and the doctor. All those are kind of a human dictated communication. And in most scenarios, it's kind of unstructured. So basically, it's a kind of a conversation that being converted into a piece of text. There's not sort of a template in most scenarios they follow. As a result, it would be hard for the next visit for the patient, for the doctor to review that history and then kind of be able to extract meaningful and relevant information with respect to the current visit. As a result, clinicians spend about 49% of their time on this paperwork, which is kind of a burnout from the time they could spend with the patient. There has been quite a bit of interest in utilizing NLP to structure the data, the textual data in the healthcare systems, such as the EHR systems, to basically leverage the information being captured in a more structured manner. Another interesting example is basically for the clinical decision support. So as an example, how far this has gone, back a few years ago, Department of Veterans Affairs used NLP to review more than 2 billion EHR documents, and they were able to successfully implement a decision support for clinicians that can help in identifying the progress of depression, potential self-harmness in veteran patients. And finally, the one that is more kind of a futuristic NLP-driven application is the Q&A system. Dr. Rasu Shrestha, Chief Innovation Officer at UPMC, developed a bunch of NLP apps that kind of can help the clinicians in a scenario of a Q&A, ask questions about a patient, and then the machine behind the scene dives into all the structured data about the patient and try to, in a very close to human language, answer those questions so that kind of, rather than like the clinician trying to dive into these textual reports that have been available for the patient. So what are different ways of doing natural language processing? So the very basic format that probably most of us are familiar with would be syntactic analysis, and that's dealing with the grammar of the language. Kind of what is a verb, what is a noun, this kind of stuff. So mostly it's a rule-based driven approach, and there has been years of linguistic work done on this. But if you think about a conversation, it's not just the fact that where the verb sitting in the sentence or where the noun sitting. That's not just going to give us all the information that is being conveyed through this piece of text. What's next would be the most interesting piece, which would be the meaning of the sentence itself. That's a semantic analysis job to help us understand the context and the meaning. Here you see an example of a Google translation from German to English. This shows like how far the AI has been able to help the natural language processing. So in this case, look at the word bank. As the person giving more context by typing, you see the translation changes. And that's just because now the machine is taking not just the word by word translation into account, but the overall context and meaning, what the person is trying to achieve through this typing into account, and that derives the translation, as you can see. Finally, the most kind of difficult of all would be the pragmatic analysis. An example of this would be a sarcasm. So in this example that I'm showing here, it's a Twitter from a person that says, wow, 35 minutes to get to a cup of coffee, great job. Well, if you look at just the words, there are positive words in there, wow and great. If you just take those into account, you will think this is a positive review about this place. Whereas like if you look at the whole thing altogether, there's a sarcasm there, so it's overall it's a negative. So the level of difficulty of doing NLP to understand this kind of basically meaning and context increases from syntactic, which is the simplest way of doing it, all the way to pragmatic analysis. What are the applications of NLP in the real world? One of the interesting recent applications that we see would be about text summarization. So in this example that I'm showing here, the person is giving a passage to the machine, and then this paragraph is being summarized as like the most important things to grab out of this paragraph. This is again related to the new advancement with the language modeling that is doable. The next application that I put here would be about, again, the machine translation. It's still an open problem. There has been a great improvement, as probably you guys have been using Google Translation. If you compare it to a few years ago, there's definitely a great improvement, but still from one language to another, there are still challenges that NLP is trying to solve. And finally, the one that I'm interested in specifically in healthcare is the name entity recognition. What does that mean? Meaning that given a piece of text, try to label or annotate this data for me in a sense of giving some predefined labels. In this case, in the example that you see here, the labels are organization, a product, and a person, and I give a piece of text, and it automatically should be able to determine what kind of label it should assign with respect to this. It's not just by the word itself that is being taken into account, the context that is happening in it is important too. An example of this in the healthcare scenario would be, let's say, considering the anatomy back. Back sometimes refers to as an anatomy, but in another context has a different meaning. So that's why it's not just very straightforward dictionary matching problem. In the context of healthcare, one of the ways that we can look at this NER application would be for anatomical phrase labeling. This is something that I've studied quite a bit. And in this example that I'm showing here, you see a piece of text from a radiology report. And there are lots of anatomical phrases that you can find in this kind of reports. Being able to label and extract these anatomical phrases from the report helps us to structure this data. So if you want to build eventually a Q&A for a radiologist, if there's a specific mention of anatomy, then we can use this structured data to narrow down to the right answer. It's not a very trivial problem to work with. As I said, the context and the meaning play a significant role. And to just give you an example, let's consider the right lobe as one anatomical phrase we want to label. Lobe is a compartment that can be referred to a part of a lung or liver, thyroid, brain. They all have lobes. Being able to say this specific case is referring to the lung versus another one that is referring to the liver is only possible if I give you the context which I'm talking about, this specific compartment in the body. So there are a number of different ways that have been proposed to solve this NER problem for the kind of a healthcare application that I mentioned before. The very basic one would be just having prepared a list of all the keywords and of possible anatomical terms, and that would be like using an ontology like SNOMED CT. Of course, that would be like helping to detect exact matches with maybe some level of flexibility around it. But of course, it's going to come to some scenarios, like this case, that I don't have literally the exact same match within my ontology. But then I can build some grammar and rules using regular expressions to extend the level of this keyword can match to different examples, but very similar. The next level would be, what if like I have something like this that has like some abbreviations that the doctors, with all due respect, make a lot of these abbreviations when they're kind of summarizing something about a patient. So I can give a machine a lot of these examples by annotating them in a big corpus of reports and then try to learn out of these many examples. But obviously it's going to be expensive because it requires a lot of labeled data, as well as it's going to be only limited to the way that these examples are given. In a sense, like not all possible scenarios is going to be able to generalize to. Let's say, for instance, the example that the abbreviation is, this is like stands for left lower lobe in lung. Again, like if I haven't seen through the examples that I provided for the machine is not able, the statistical machine learning is not able to generalize to detect unseen data. That's where the deep learning started to show a very good improvement in providing capability to deal with such scenarios. And those are like the RNN networks, the CNN networks, and all the recent advancements that we see being utilized for healthcare. So since the introduction of these approaches in deep learning into the kind of a natural language processing domain, looking at the publications, at least as a mean of the progress in the domain, you see that there has been a big jump since 2013, and I'm going to show why exactly we see this. But I assume like it's a 2 years old data, but I assume like it's really climbing rapidly in a sense that there's so much advancement that I'm going to review some of those in this talk. So all the kind of advancement that we started to see in 2013 are thanks to a work by our Google colleagues that they introduced this word embedding, distributed word embedding representations. This is typically, if you want to look at it as a way of telling the machine what is a good representation for a piece of string. Obviously, we don't want to give the string as a character by character as the input to a machine. What we do, we try to map it to a vector space. A mathematical representation consists of a vector, and then that's what's going to be the input to the machine learning framework to start with. Mikolov introduced the word-to-vec approach, which is a very interesting way of solving this problem of finding this mapping from strings to this real value vector representation, and which does not require label data. Why? Because the label data is the fact that the sentences have a sequence order in them. The word happen in a specific sequence. So the way he designed the network is that you give like a sentence, every of these input points is going to be a string basically in a given sentence, and then you can start with a one-hot vector. So basically you make a big vector the size of the vocabulary in the language and only has one at the specific location of that specific word in the vocabulary. The rest of them is going to be zero. You start with such high dimensional vector representation. Then your task is basically given a specific word, what kind of context that word occur in. That's one way of doing it. The other way would be I give you a context and a word is missing from that context. Tell me what is that word or predict that word. So these are two ways of doing and learning that word embedding representation. What's happening is that even though the network is trained to do the prediction for you, either given the word, give me the context, or given the context, give me the word, what you get out of this is basically this matrix in the middle, which is the vector representation for every word. But rather than the one-hot vector representation would be very high dimensional, you're reducing it to the number of the the vector size that you define as a parameter to your basic neural network in this scenario. So typical sizes would be 64, 256, 512, depending on how much level of details you want to capture with this scenario. So this kind of approach to get to a vector representation made things quite a bit of advancement in the natural language processing. And since then, we see a big jump in the performances, all the kind of NLP tasks that have been kind of benchmarked against by introduction of the word-to-vec, we see a good jump there. So in the case of healthcare, I took all those basically vector, the way of vector representation. I take an ontology in healthcare such as SNOMED. All the terms within that, I try to map it using this vector representation. And I just collapsed all those, let's say 512 vector sizes into just two dimensions so I can visualize it. So every circle in this plot is an anatomical term within the SNOMED ontology. You see, by doing just purely giving the sentences out of this ontology to the word-to-vec method, I can learn a representation that puts the words that belong to a similar anatomy into kind of a similar cluster in this vector space. So the anatomical terms that are related to the lung all sit next together like a nice cluster there, and the prostate ones there, as well as the breast in this area. And if you have a new word, let's say, that you haven't seen before, which with the previous techniques we couldn't give a label to, but by doing this, I can just find a vector representation for it, let's say segment 4, and see where in this space this vector sits closest to these anatomical areas in the body. If you do that, you will see that based on the similarity of these two vectors, it sits very close to the liver. But then we set the example that I showed before. What about lobe? So this is the shortcoming of this word-to-vec approach as well, because you build a fixed word embedding representation for words. So if the word lobe in the corpus that you train your network with occurs the most with liver, it's going to learn a representation close to liver. But if the context changes to lung, it's not going to adapt accordingly. So that's the main shortcoming of this word-to-vec approach. That's where the people start thinking about contextual word embedding. So meaning that a word embedding representation, a vector representation that dynamically changes as the context changes. So you get a different representation if you switch the context. That's where the Allen NLP guys in 2018 introduced the ELMO approach. So basically, what Elmo approach is doing is taking advantage of the RNN networks, LSTM flavor, which is basically a sec-to-sec, sequence-to-sequence kind of a network. And they put together a backward language model and a forward language model. But quickly I tell you, what does the language model mean? A language model refers to a network that basically tries to predict what's the next word or what is the previous word. So if you're doing the forward language model, your task is to say what is the next word. So it's a bit small, but if you look at this example, I have the nodule is in the lung, and then the goal of this network is to predict what word comes after lung. In the backward language model, you're trying to predict what is the word previous to the first node. So this way, the two kind of models try to learn a representation given this basically sentence to start with. But then the good thing is that the way that you put these two together plus a word embedding representation to make it contextually different as the context is getting different meanings is to start with a big corpus of unlabeled data. Any kind of corpus would do. You train your Elmo model, you do both basically these three pieces together, and now you just erase the last fully connected layer. And now you have a specific task that you want to learn the embedding for, a word embedding for, and you just have a limited supervised training to be done. So you only need a small sample size of labeled data for the specific task. And then you retrain your network, fixing the other parameters in the network, and then there you will be able to create a contextual, dynamically changing word embedding representation based on your specific application. So that was the beauty of Elmo approach. The shortcoming of the Elmo was the fact that it still doesn't have much of capability to learn long-range dependencies. So assume the example I gave you, the word loop happens 4 sentences after we talk about long. So Elmo is going to struggle to make the connection that I'm still talking about the long in the 5th sentence when I refer to a loop. So that would be one shortcoming. The other shortcoming is the fact of the parallelization. We know the computation of these things can be very heavy. So if there are no ways to parallelize the computation, this is just not going to be realistic to implement something like this. And this is due to the fact that the RNNs are sequential networks. So that's where the transformers were introduced by a paper as attention is all you need. What happens is that rather than you say, I give you the whole context as a sequence of words, I'm going to also tell you where to put your attention. So there's a long, and 4 sentences before, you need to put your attention on that long word when you're trying to learn word embedding representation. So this kind of a animation is showing that for every layer, basically, I'm taking into account the context from the other words, but eventually the nodes get more and more focused on where about the kind of attention should sit. So transformers were basically an architecture that kind of trying to solve the problem of long-range dependencies by taking this attention mechanism to help. Also, for the sake of dealing with the parallelization, we start using the convolutional neural networks. As we know, they're very good for the parallelization. At this point, again, Google pioneered some work recently that is referred to as BERT. I'm going to talk about it. This is the most advanced language modeling technique. But before that, to appreciate how transformers work and kind of deal with the dependency and the attention, just look at this specific example. So the first sentence says, the animal didn't cross the street because it was too tired. So where does this it refer to? What other noun in this sentence does it refer to? Animal, right? So what about the next sentence? The animal didn't cross the street because it was too wide. What about this it? To the street, right? So if you look at the way the layers of the transformer and trying to interpret it in a sense that showing which of the words in the sentence are getting the attention when I'm looking at this it, you'll see nicely it's kind of giving the highest weight into the animal rather than the street, whereas the second sentence that the word street is getting the highest weight of attention. So this is all learned through the mechanism of training a transformer model. So taking advantage of these capabilities, BERT was introduced by Google in 2018. It's a bidirectional encoder representation. The architecture is built on top of the transformers, and the original BERT that they proposed was trained on the entire Wikipedia as well as book corpuses, about 800 million words. So it's a very deep bidirectional model, and as a result, the complexity, the number of parameters you need to learn is much, much higher. It's about 116 million parameters you're trying to learn. So as you can imagine, computationally, this is going to be expensive. So after BERT was introduced, shortly after in 2019, Albert came out, which is probably 1 week old or 2 weeks old. It hasn't been presented at the conference yet. It's just on archive. The paper is available. It's a light BERT. That's what it stands for, the light BERT. And they try to factorize some of the parameter tuning to kind of speed up the process, as well as they changed the task of rather than learning sentence prediction to the sentence location prediction. So these two significantly improve the speed of training a BERT. Just in this plot, I'm trying to show the complexity where the NLP is going in terms of like the computation. The ResNet, which is an image-based kind of task, it sits about 26 million parameters you're trying to optimize. As you can see with transformers and with the BERT, we are moving towards a much, much higher number of parameters we're trying to optimize, which is interesting to think about it, but that like the language has such complexity that requires these many parameters to learn from. And this is where we are currently sitting at. For a chatbot or for email auto-completion, probably you guys have noticed in Gmail, if you use Gmail, the auto-completion doing a great job. It's because there's these many parameters learned to be able to provide such capability. And that's one of the reasons is because the hardware also is capable of doing such a thing. So Google is taking advantage of TPUs, so basically tensor processing units versus GPUs. And the good thing about the TPUs is that it makes the computation of matrices much, much faster. So as a result, that's what exactly these parameter tuning networks require. And it has been shown that, for instance, for training a BERT model, you can do it from 32 to 54% faster training versus using GPUs architecture. Just to give you an idea, how long does it take to train a BERT model? If you just use your own desktop at home, let's say with 4 GPUs, it's going to take you to train a BERT large, which is about 24 layers. It's going to take you 68 days to train that model. If you want to do the BERT base, which is 12 layers, half of that is going to take half of the time. If you use a 8 GPU machine, such as taking advantage of this type of GPUs, is going to range between 21 to 34 days to train a BERT large model. And if you're using the cluster of GPUs, you can bring it down to about 5 days. Recently, NVIDIA announced that using their kind of cluster for GPU training, you can bring this down to 47 minutes. Now we're talking that this is possible to use it for real-time applications or close to real-time applications. So this is a great improvement in terms of the hardware to accelerate the utilization of such NLP advancement, and definitely in healthcare is going to have a big impact as it's required to work almost in real time to be able to be useful. So where are we now? What is left to do? Still, healthcare for NLP needs to deal with a lot of challenges. The size of the data that we're dealing with on a daily basis, megabytes of data is being added to the databases in hospitals. And all those data are, as I said, unstructured, needs to be structured to be able to use it in a clinical scenario. The format of the data, that's a big headache currently. Like data being captured from different vendors, they come with different formats, and as a result, it's hard to normalize the process to analyze that data. The structure There's no structure, so definitely that's a big challenge there. And there's a longitudinality to the data. So the data is longitudinally related to each other. Being able to extract and connect the dots, that's a very hard problem in NLP at this point. And then, as I said, the complexity of the language they use in the clinical scenario is another big headache for people doing NLP in healthcare. There's not much of a grammar that's being followed, or there's kind of telegraphic way of talking about things for instance, in a radiology report. That makes it all very different than a general domain NLP task, like looking at the Google News articles, for instance. The ambiguity of the language in terms of speculations, negations, R/O stands for rule out. So you need to kind of learn this language and different ways of showing the negation, showing the speculation. This is unique to the specific domain. And finally, there's the part that is the most challenging to learn. That would be the domain knowledge, being able to extract the domain knowledge, not just by books, by learning by experience from talking to the radiologist and kind of capturing that experience and trying to model it and teach it to a machine. I find that that's the most challenging piece. So with that, I'll conclude my talk, and I hope that gives you some kind of a
couple questions.
So is the language processing used in healthcare to improve patient outcome or improve RCM? Can you tell us?
What do you mean by RCM?
Revenue cycle management?
So it depends. Like I only mentioned a few kind of applications for NLP. The applications could vast from like different kind of like from patient side all the way to the revenue side. So I think it depends what kind of context you want to look at it. In all scenarios, I find like companies dedicated efforts to utilize NLP for that sake. But at the end of the day, I think it's definitely going to save time, it's going to save costs, and as well as better outcomes for the patients.
Next question.
So do you have any examples of mature applications of NLP in healthcare that people are using in production, proven results?
Sure, I tried to put a few in the beginning of the slides. For instance, there are some pioneer work, not much scalable yet. And the reason is that the data looks very different from one clinical setting to another, from one domain to another. Let's say if you do something in radiology, trying to do the same thing, using the same technology or models you train, but for pathology is not just straightforward. So you need some domain adaptation. But there are some examples, domain-specific applications that are very successful.
Thanks, Amir. Great presentation.
Thank you.
Okay, our next presenter is Richard Dutton from Google. He's a head of ML and AI in corporate Google. Thanks, Rich.
Thank you.